close your eyes. Tonight, I want you to picture something very specific. You are outside, somewhere far from the noise of the world. Maybe on a balcony overlooking a quiet valley. Maybe on a blanket spread across a field. Maybe just at your window with the lights turned off and the curtain pulled back. It does not matter where. What matters is the sky. Because the sky is clear tonight, and the stars are out. Not the dim, washed-out handful you might see from a city street. The real stars. Thousands of them. Tens of thousands. A sky so full of light that the darkness between the stars almost disappears. The Milky Way stretches overhead like a river of powdered diamond, and you can feel, in some deep and wordless way, that the universe is very, very large. Now, I want you to find a particular star. It is not the brightest in the sky, but it is close. If you are in the southern hemisphere, you will find it easily, a golden point of light in the constellation Centaurus, part of a pair of stars that ancient navigators used to find their way across the sea. If you are in the northern hemisphere, it sits low on the horizon, sometimes hidden by the curve of the Earth itself. This star is called Alpha Centauri, and it is special, not because it is particularly large, not because it is particularly old, not because it burns with any unusual color or intensity. It is special for a much simpler reason. It is the closest star to our sun. Think about that for a moment. The closest star. Out of all the stars in the sky, all the suns you have ever seen on any clear night, this one is the nearest. Every other point of light up there is farther away. Every other star you can name, Sirius, Vega, Polaris, Betelgeuse, is more distant. Alpha Centauri is first in line, the front door of the cosmic neighborhood. And here is something else worth knowing. The light you are seeing from Alpha Centauri right now, the photons that are entering your eyes at this very moment, left the surface of that star about 4 years ago. They have been traveling through the void at 300,000 kilometers per second, the fastest speed anything in the universe can travel, and it still took them more than 4 years to reach you. That faint golden glow is not a live image. It is a memory, a 4-year-old postcard from the nearest sun. And if anything has changed at Alpha Centauri since those photons departed, you will not know about it for years. This is the nature of starlight. Every star you see is a window into the past. The further away the star, the older the light. When you look at the night sky, you are not seeing the universe as it is. You are seeing the universe as it was. Moments ago for the nearest stars. Years ago for most of them. Thousands of years ago for the faintest ones. The night sky is a time machine, and every photon is a messenger that has been traveling in silence across the void, carrying news from a star that may or may not still be shining by the time the message arrives. But Alpha Centauri's message is the freshest. 4 years. That is all. In cosmic terms, that is almost real time. Almost close enough to touch. Almost. Of all the hundreds of billions of stars in our galaxy, of all the countless suns burning in every direction across the Milky Way, Alpha Centauri is our nearest neighbor, the one right next door, the porch light at the end of the cosmic block. And for as long as humanity has dreamed of reaching the stars, Alpha Centauri has been the obvious first destination. If we are ever going to leave our solar system, if we are ever going to set foot on a world orbiting another sun, this is where we would go first. It is, by cosmic standards, tantalizingly close, just 4.24 light-years away. In a galaxy that is 100,000 light-years across, Alpha Centauri is practically touching us. It is right there, a stone's throw, a neighbor leaning over the fence. And yet, here is the thing that will stay with you long after this video ends. That distance, 4.24 light-years, is not small. It is not close. It is not a stone's throw. When you convert those light-years into miles, when you do the actual math, the number that appears is so large that the human mind simply cannot hold it. It is a number that breaks your intuition, a number that turns the nearest star from a friendly neighbor into an unreachable island surrounded by an ocean of nothing. 25 trillion miles. That is how far Alpha Centauri is from Earth. 25 trillion. 25 followed by 12 zeros. A distance so vast that if you started walking toward it right now at a brisk pace and you never stopped, never rested, never slept, never aged, never died, it would take you roughly 850 million years to arrive. And that is where our story begins tonight, with the star that should be closest, the star that should be easiest to reach, the star that sits right next door in a galaxy of 400 billion stars. Because if even Alpha Centauri is this far away, then the universe is telling us something. Something profound, something beautiful, and something deeply, quietly terrifying. Before we go any further, I want to say something. If you enjoy falling asleep to these journeys through the cosmos, consider subscribing to the Science Pillow. Every week, a new documentary arrives designed to carry you gently through the wonders of the universe and into a peaceful sleep. All you need to do is press the subscribe button, and the stars will be waiting for you every night. You do not need to stay awake. You do not need to take notes. Just lie back, close your eyes, and let the universe do the rest. Now, let us begin. Tonight, we are going to take a journey to Alpha Centauri. Not a quick overview, not a summary, a real journey. We are going to start with the star system itself, this family of 3 suns that orbits in the cosmic darkness just beyond our reach. We are going to learn who discovered them, what they look like, and what worlds they might harbor. Then we are going to confront the distance. And this is where the story becomes extraordinary. Because 4.24 light-years sounds like a number, but when you translate it into human terms, into miles and hours and lifetimes, it becomes something else entirely. It becomes a wall. An invisible, silent, absolute wall that separates us from everything beyond our own sun. We are going to explore every idea humanity has ever had for crossing that wall. From the chemical rockets that carried us to the moon, to nuclear explosions, to sails made of light, to engines that burn the same fuel as the stars themselves. We are going to dream big, and then we are going to confront, honestly and gently, the limits of those dreams. And finally, we are going to imagine arriving, standing on a world that orbits another star, looking up at an alien sky, and looking back toward home, where our own sun is nothing but a faint yellow dot among thousands of others, a dot you could cover with your thumb. That is where we are going tonight, all the way to Alpha Centauri, and all the way back. So settle in. Let the weight of the day dissolve, and let us start with the stars themselves. Section 2. A family of suns. To understand Alpha Centauri, you first need to know that it is not a single star. It is a family, a system of 3 stars bound together by gravity, orbiting each other in a slow, ancient dance that has continued for billions of years. The first 2 members of this family are called Alpha Centauri A and Alpha Centauri B. They are a binary pair, two stars that orbit each other the way the Earth orbits the Sun, except their orbit is not circular. It is a long, stretched-out ellipse that takes roughly 80 years to complete. At their closest approach, they are about 11 astronomical units apart, roughly the distance from the Sun to Saturn. At their farthest, they swing out to nearly 36 astronomical units, almost the distance from the Sun to Pluto. These two stars have been known to humanity for thousands of years. Ancient Egyptian astronomers recorded their light. Aboriginal Australians incorporated them into their stories of the sky. Chinese astronomers in the 3rd century catalogued them as a single bright point in the southern heavens. For most of human history, they appeared as one star, a single golden light in the constellation Centaurus, the second brightest object in the night sky, after the two components of the Centaurus constellation appeared as a single point to the naked eye. It was not until 1689 that the Jesuit astronomer Jean Richaud, observing a comet from Puducherry in India, noticed that the bright star Alpha Centauri was not one star but two. His telescope revealed what the naked eye could not: two points of light orbiting each other, separated by a tiny gap that no unaided eye could detect. It was one of the earliest discoveries of a binary star system, and it changed how astronomers understood the cosmos. Stars were not all solitary wanderers. Some traveled in pairs, some in families. Alpha Centauri A is the larger and brighter of the two main stars. It is a G-type main sequence star, which is the same classification as our Sun. If you could stand on a planet orbiting Alpha Centauri A and look up, you would see a star that looked remarkably similar to the one that warms your face on a summer morning. It is slightly larger than the Sun, about 10% more massive, and about 50% more luminous. Its surface temperature is roughly 5,790 kelvins, compared to the Sun's 5,770. It burns with a warm, golden yellow light, and it is roughly 6 billion years old, about 1.5 billion years older than our own star. In many ways, Alpha Centauri A is the Sun's twin. Not identical, but close enough that astronomers have long wondered whether it might host planets similar to Earth. A world orbiting Alpha Centauri A at the right distance, in the sweet spot where water can exist as a liquid on the surface, might look and feel remarkably like home. Alpha Centauri B is the smaller, cooler sibling. It is a K-type star, slightly less massive than the Sun at about 90% of the Sun's mass, and significantly dimmer, shining with only about half the Sun's luminosity. Its surface temperature is roughly 5,260 kelvins, which gives it a warm, slightly orange tint compared to the yellow of its companion. If you could see them side by side, Alpha Centauri A would look like a golden coin, and Alpha Centauri B would look like a slightly smaller, slightly redder copper penny. But do not underestimate Alpha Centauri B. It is still a perfectly ordinary, healthy, stable star. It has been burning hydrogen in its core for roughly the same 6 billion years as its larger partner. It is capable of warming planets. It is capable of sustaining habitable zones. And for a potential civilization looking for a home, it would be a perfectly fine sun. Together, Alpha Centauri A and B form one of the most studied binary star systems in the history of astronomy. Their orbit has been tracked for centuries. Their masses, their luminosities, their temperatures, their chemical compositions have all been measured with extraordinary precision. We know more about these two stars than almost any others in the galaxy, for the simple reason that they are so close. And the dance between them is beautiful. Over the course of their 80-year orbit, the two stars sweep through a vast ellipse, sometimes drawing close enough that their gravitational influence on each other becomes significant, sometimes drifting apart until they appear, even through a telescope, as two entirely separate points of light. In 2016, they reached their closest approach, periastron, separated by only about 11 astronomical units. By 2075, they will have swung to their farthest separation, nearly 36 astronomical units apart, before slowly drawing together again. This orbital dance has profound implications for any planets in the system. A binary star system is a more complex gravitational environment than a single star system like ours. Planets orbiting one star must contend with the gravitational pull of the other. If a planet orbits too far from its host star, the companion star's gravity can destabilize its orbit, sending it careening into the void or crashing into one of the stars. This limits the habitable zone of each star to a region relatively close in, where the gravitational influence of the partner is still manageable. Computer simulations have shown that stable planetary orbits are possible around either Alpha Centauri A or Alpha Centauri B, provided the planets orbit within roughly 3 to 4 astronomical units of their host star. This is well within the range where Earth-like planets could exist. But detecting such planets is extraordinarily difficult. The glare of two bright stars so close together makes it challenging to pick out the faint signal of a small, rocky world. Several candidate detections have been announced over the years, but none have been confirmed beyond doubt. In 2012, a team of European astronomers announced the detection of an Earth-mass planet orbiting Alpha Centauri b, designated Alpha Centauri bb. The discovery made headlines around the world, but within 2 years, further analysis revealed that the signal was likely a statistical artifact, a ghost in the data rather than a real planet. The announcement was retracted. It was a reminder of how difficult this work is and how easy it is to see patterns where none exist when the stakes are high and the desire to find something is so strong. The search continues, and the question of whether Alpha Centauri A or B harbors rocky, potentially habitable worlds remains one of the most tantalizing open questions in exoplanet science. But there is a third member of the family. A quiet, dim, almost invisible companion that was not discovered until 1915. And it is this third star, the runt of the family, the smallest and faintest of the three, that holds the greatest secrets. Its name is Proxima Centauri. In 1915, a Scottish astronomer named Robert Innes was working at the Union Observatory in Johannesburg, South Africa. Innes had been studying the proper motion of stars, the tiny apparent movement of stars across the sky that occurs because both the stars and our solar system are moving through the galaxy. Stars that are closer to us appear to move faster, the way a nearby car seems to zip past you while a distant mountain appears to stand still. Innes noticed a faint red star very close to Alpha Centauri A and B that had an unusually large proper motion. When he measured its parallax, the tiny shift in its apparent position caused by Earth's orbit around the Sun, he realized something extraordinary. This faint red star was even closer to us than Alpha Centauri A and B. By a small but measurable amount, this dim little point of light was the nearest star to our Sun. He called it Proxima Centauri. Proxima from the Latin word for nearest, the closest star. Proxima Centauri is nothing like its larger companions. It is a red dwarf, a type of star so small and so dim that it is completely invisible to the naked eye despite being the closest star to our solar system. It has roughly 12% the mass of the Sun. Its diameter is only about 14% of the Sun's diameter. If the Sun were a basketball, Proxima Centauri would be a golf ball, and its luminosity is astonishing in its feebleness. Proxima Centauri shines with roughly 1/6 of 1% of the Sun's light. You would need more than 600 Proxima Centauris to produce the same amount of light as one Sun. It is a cool star with a surface temperature of only about 3040 kelvins, less than half the temperature of the Sun's surface. This low temperature gives it a deep, dusky red color, like the last ember in a dying fire. If you could see it from nearby, it would not look like the brilliant golden disk of our Sun. It would look like a dim red lamp hanging in the darkness. But what Proxima Centauri lacks in size and brightness, it makes up for in longevity. Red dwarfs are the most efficient stars in the universe. They burn their hydrogen fuel so slowly, so carefully, that they can shine for trillions of years. Our Sun will exhaust its fuel in roughly 5 billion years. Proxima Centauri will continue burning for 4 trillion years. That is nearly 300 times the current age of the universe. Long after every Sun-like star in the galaxy has died and gone dark, Proxima Centauri will still be there, glowing faintly in the void, a patient ember in an increasingly empty sky. And red dwarfs are not rare. They are, in fact, the most common type of star in the Milky Way. Roughly 70 to 80% of all stars in our galaxy are red dwarfs. Most of them are too dim to see with the naked eye. They are the quiet majority, the invisible backbone of the galaxy. But Proxima Centauri has a darker side, a side that makes it a dangerous star to live near. Red dwarfs, despite their small size and cool temperatures, are among the most violently active stars in the universe. Proxima Centauri is what astronomers call a flare star. Its surface is prone to sudden, violent eruptions of magnetic energy that can increase its brightness by several times in a matter of seconds. In March of 2017, astronomers using the Atacama Large Millimeter Array in Chile detected a superflare from Proxima Centauri. In the span of 10 seconds, the star's brightness increased by a factor of 1,000. 1,000 times brighter. For a brief moment, this dim little red dwarf, normally invisible to the naked eye, blazed with enough energy to sterilize any unprotected surface within its habitable zone. These flares are not rare. They happen regularly. Some studies have estimated that Proxima Centauri produces significant flares several times a day. Each flare releases a burst of ultraviolet and X-ray radiation that would be lethal to any unprotected life on a nearby planet. The flares also produce coronal mass ejections, vast clouds of charged particles that slam into any planet in their path, stripping away atmospheric gases and eroding any magnetic shield. For a planet orbiting close to Proxima Centauri, which any planet in the habitable zone must do because the star is so dim, these flares are a constant, relentless bombardment. The habitable zone of Proxima Centauri is very close to the star, about 1/20th of the distance from the Earth to the Sun. At that distance, the planet is tidally locked, meaning one side permanently faces the star and the other side permanently faces away, locked in eternal darkness. And, at that distance, the flares hit with devastating force. This is the paradox of Proxima Centauri. The closest star, the nearest, potential home, and one of the most violent, most dangerous stellar environments we know of. But despite all of that violence, despite the flares and the radiation and the constant stellar storms, Proxima Centauri harbors something extraordinary. Something that was discovered in 2016 and sent a wave of excitement through the entire scientific community. It has a planet. A rocky, Earth-sized planet, sitting right in the habitable zone. The discovery was made through a campaign called Pale Red Dot, led by the astronomer Guillaume Anglada-Escude at Queen Mary University of London. The name was a deliberate echo of Carl Sagan's famous description of Earth as a pale blue dot, and it captured the poetry of the search. A pale red dot, orbiting a pale red star at the nearest point in the cosmos. The technique they used is called radial velocity, or the wobble method. When a planet orbits a star, the planet's gravity tugs on the star, causing it to wobble very slightly. This wobble is tiny, just a few meters per second for an Earth-sized planet, but it can be detected by measuring the Doppler shift of the star's light. When the star moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, it shifts toward the red. Anglada-Escude and his team observed Proxima Centauri for 60 nights, using the HARPS spectrograph at the European Southern Observatory's telescope in La Silla, Chile. They also incorporated data from previous observation campaigns stretching back to 2000. Night after night, they measured the tiny wobbles in Proxima Centauri's light, looking for a repeating pattern that would indicate the gravitational pull of an orbiting planet. And they found it. A clear, consistent signal with a period of 11.186 days. A wobble that could only be explained by a planet with a minimum mass of about 1.17 Earth masses, orbiting at a distance of roughly 0.0485 astronomical units from the star. The planet was named Proxima Centauri b, and it was in the habitable zone. The announcement was made on August 24, 2016, in a paper published in the journal Nature. The news rippled through the world's media like a shockwave. The nearest star to our sun had a planet, and not just any planet. A rocky, Earth-sized world in the zone where liquid water could theoretically exist on the surface. The implications were staggering. If we ever wanted to send a spacecraft to another star, if we ever wanted to study an exoplanet up close, we would not have to travel to some distant corner of the galaxy. The target was right next door, 4.24 light-years away, the absolute nearest point in the cosmos where another world might harbor conditions friendly to life. But the excitement was tempered by caution. Being in the habitable zone does not mean a planet is habitable. It means that the planet receives enough energy from its star for liquid water to potentially exist on the surface. But liquid water requires an atmosphere, and whether Proxima b has an atmosphere is, to this day, an open question. The problem, as we discussed, is the flares. Proxima Centauri is a violent star. Its superflares would blast any unprotected atmosphere with extreme ultraviolet and X-ray radiation, breaking apart atmospheric molecules and allowing them to escape into space. Over billions of years, this process could strip a planet completely bare, leaving it as airless and lifeless as the Moon. But there are scenarios where an atmosphere could survive. If Proxima b has a strong magnetic field, generated by a molten iron core like Earth's, that field could deflect the worst of the stellar wind and protect the atmosphere. Some models suggest that a planet with a magnetic field roughly as strong as Earth's could retain a substantial atmosphere even around a flare star. Other models are less optimistic. Another possibility is that Proxima b started with a much thicker atmosphere than Earth, perhaps a dense blanket of carbon dioxide and water vapor, and even after billions of years of erosion, enough remains to support liquid water. A planet that begins with 10 times Earth's atmospheric mass could afford to lose 90% of it and still have an atmosphere comparable to our own. The James Webb Space Telescope has observed the TRAPPIST-1 system, another set of rocky planets orbiting a red dwarf, and found that at least some of those worlds appear to have lost their atmospheres entirely. This is not encouraging for Proxima b. But every star system is different, every planet is different, and the question remains genuinely open. There is another complication. Proxima b is almost certainly tidally locked. This means that its rotation period matches its orbital period, so one side of the planet always faces the star and the other side always faces away, just as the moon always shows. The same face to Earth, Proxima b always shows the same face to Proxima Centauri. This creates a world of extremes. The day side, the hemisphere permanently facing the star, would be bathed in constant, ruddy red light. The night side, forever turned away, would be locked in permanent, freezing darkness. The temperature difference between the two hemispheres could be enormous, potentially hundreds of degrees. But between these two extremes, there is a narrow band, a ring of permanent twilight that encircles the planet at the boundary between day and night. Astronomers call this the terminator zone, and it is here, in this slender ribbon of eternal dusk, that conditions might be most favorable for liquid water, and, perhaps, for life. In the terminator zone, the light would be dim and reddish, filtering in at a low angle from the star that hangs forever on the horizon. The temperature would be moderate, cooled by the proximity of the frozen night side, and warmed by the glow of the perpetual day side. If there is an atmosphere thick enough to circulate heat from one hemisphere to the other, the terminator zone could be surprisingly comfortable. Not warm, perhaps, not bright, but livable. Picture it, a world where the sun never rises and never sets, where the sky on one side glows with a deep, eternal crimson, and the sky on the other side is black and filled with stars, where the wind blows constantly from the cold side to the warm side, carrying moisture that falls as rain or snow along the twilight border. A world of permanent dusk. A world that looks nothing like Earth, and yet might, in some strange and alien way, be capable of supporting life. This is Proxima Centauri b, the closest known exoplanet, the world next door. And it is separated from us by an ocean of emptiness so vast that reaching it may be the single greatest challenge our species will ever face. Since the discovery of Proxima b, astronomers have found hints of additional planets in the system. Proxima c, announced in 2020, is a candidate planet with a mass roughly 7 times that of Earth, orbiting much farther out with a period of about 1,928 days. If confirmed, it would be a cold super-Earth or mini-Neptune, far too distant from the star for liquid water, drifting in the outer reaches of the system where temperatures plunge far below freezing. Proxima d, announced in 2022, is even more intriguing in some ways. It is tiny, with a minimum mass of just 1/4 of Earth's mass, making it one of the lightest exoplanets ever detected. But it orbits extremely close to the star, with a period of only 5.122 days, Well inside the habitable zone on the hot side. Its surface, if it has one, would be scorched by the nearby star. 3 planets, perhaps more waiting to be found. A solar system right next door with at least one world that might, just might, have the right conditions for life. The nearest interstellar destination. The first place we would go if we could go anywhere. And that "if" is the heaviest word in this entire story. Section 3. 25 trillion miles. Let us talk about distance, real distance, not the abstract, poetic distance of light years and astronomical units, but the gut-wrenching, mind-breaking, soul-crushing distance that separates us from Alpha Centauri in terms that a human being can actually feel. 4.24 light years. It sounds almost manageable. 4 and a bit, a small number. You can count to 4 on one hand. Light years are just a unit, like miles or kilometers, and 4 of anything does not sound like very much. But a light year is not like a mile. A light year is the distance that light travels in 1 year, and light is the fastest thing in the universe. Nothing moves faster. Nothing can move faster, as far as we know. Light travels at 299,792 kilometers per second. That is 186,282 miles per second. In 1 second, a beam of light could travel around the Earth's equator 7.5 times. In 1 minute, light crosses roughly 18 million kilometers. In 1 hour, roughly 1 billion kilometers. In 1 day, roughly 26 billion kilometers. And in 1 year, light covers a distance of 9.46 trillion kilometers. That is 5.88 trillion miles. 1 light year is 5.88 trillion miles. And Alpha Centauri is 4.24 of those. When you multiply it out, the distance from Earth to Alpha Centauri is approximately 40.14 trillion kilometers, or about 25.26 trillion miles, 25 trillion miles. Let that number sit in your mind for a moment. Not 25,000, not 25 million, not 25 billion, 25 trillion. Numbers this large lose their meaning. The human brain evolved to understand distances of a few miles, maybe a few hundred. We can intuit the length of a football field, the height of a mountain, the width of an ocean. But 25 trillion miles is so far beyond our experience that it becomes just noise. A string of digits, a number on a page. So let us try to make it real. Let us build some bridges between this number and the world you actually live in. Imagine shrinking the entire solar system down to a scale you can hold in your hands. In this model, the sun is a bright, warm marble, about 1 inch in diameter. Earth is a tiny grain of sand, almost too small to see, orbiting about 9 feet away from the marble. Jupiter is a small pea at about 45 feet. Neptune, the outermost major planet, is a peppercorn roughly 270 feet away. The entire solar system, from the Sun to Neptune, fits inside a 300-foot circle. You could lay it out in a parking lot. Now, in this same model, where the Sun is a 1-inch marble and the entire solar system fits in a parking lot, how far away would Alpha Centauri be? 450 miles. Not 450 feet. Not 450 yards. 450 miles. In a model where the solar system is the size of a parking lot, the nearest star is the distance from New York to Cleveland. That is how empty space is. That is how far apart stars really are. And remember, this is the nearest one. Here is another way to think about it. Imagine you are standing in a vast, flat, empty desert. The sun is a glowing beach ball at your feet. Earth is a tiny speck, a grain of table salt, sitting about 26 meters away. That is 85 feet. You could throw a stone from the sun to the Earth in this model. Mars is a slightly smaller grain of salt about 40 meters away. Jupiter is a marble at 135 meters. You could still see it from the sun if the air was clear. Saturn, another marble, is at 248 meters. And Neptune, the most distant major planet, is a smaller marble about 780 meters away. Less than half a mile. You could walk there in 10 minutes. The Voyager 1 spacecraft, the most distant human-made object, has been traveling for nearly 50 years. In this model, it has reached a distance of about 3.6 kilometers from the beach ball sun. About 2 miles. A pleasant afternoon walk. Now, where is Alpha Centauri in this model? 7,000 kilometers away. 7,000 kilometers. From a beach ball sun with a grain of salt Earth 26 meters away, the nearest star is 7,000 kilometers distant. That is roughly the distance from London to Mumbai, from New York to Tokyo, from one side of the Pacific Ocean to the other. Voyager, after 50 years of travel, has covered 3.6 kilometers of that 7,000. It has completed roughly 1/20,000th of the journey. If Voyager were a person walking from New York to Tokyo, it would have taken one step. One single step. After 50 years. This is the scale of interstellar space. This is what 4.24 light-years means in terms you can feel in your bones. The stars are not just far away. They are far away in a way that makes every other distance humanity has ever confronted look like a rounding error. Let us try another way to feel the distance. Let us use time, because time is something we all understand. We know what an hour feels like, a day, a year, a lifetime. Time is the ruler we measure our lives against. So how long would it take to travel to Alpha Centauri at various speeds? Let us start with walking. A brisk walking pace is about 5 kilometers per hour. If you could walk to Alpha Centauri, walking day and night without stopping, without sleeping, without aging, it would take you roughly 850 million years. That is nearly 1 billion years. 4 times longer than the age of complex animal life on Earth. You would have to start walking before the first fish crawled onto land, before the first dinosaur hatched, before the first mammal drew breath, and you would still not be there. What about driving? At highway speed, say 100 kilometers per hour, the trip would take approximately 45 million years. If you had started driving when the dinosaurs went extinct, 66 million years ago, you would be about 2/3 of the way there by now, still millions of years short. A commercial airplane flies at about 900 kilometers per hour. At that speed, the journey would take roughly 5 million years. 5 million years ago, our ancestors were just beginning to walk upright on the African savanna. They had not yet discovered fire. They had not yet spoken a word. And if one of them had somehow boarded a jet airplane at that moment and flown toward Alpha Centauri without stopping, they would be arriving right about now. The speed of sound, roughly 1,235 kilometers per hour, does not help much. At the speed of sound, the trip takes about 3.7 million years. What about a bullet? A high-powered rifle bullet travels at roughly 1,200 meters per second, or about 4,320 kilometers per hour. At bullet speed, you would arrive at Alpha Centauri in approximately 1 million years, 1 million years, a timescale so vast that entire species evolve and go extinct within it. 1 million years ago, Homo erectus roamed the Earth. Modern humans did not yet exist. Now let us move to spacecraft, the fastest objects humanity has ever built. Voyager 1, launched in 1977, is currently the most distant human-made object. It has been traveling for nearly 5 decades and is now about 24 billion kilometers from Earth, beyond the boundary of the solar system in interstellar space. It is moving at roughly 17 kilometers per second, or about 61,200 kilometers per hour. This is extraordinarily fast by everyday standards. A car traveling at that speed would cross the entire United States in about 4 minutes. But even at the speed of Voyager 1, the journey to Alpha Centauri would take approximately 73,000 years. 73,000 years. To put that in perspective, 73,000 years ago, modern humans were living in small bands of hunter-gatherers in Africa. They had not yet migrated to Europe. They had not yet painted the caves of Lascaux. They had not yet invented agriculture, writing, mathematics, or any of the things we associate with civilization. If a Voyager-like spacecraft had been launched from Earth at that time by one of those early human bands, it would be arriving at Alpha Centauri right about now. And every human who launched it, every generation of every descendant, every civilization that rose and fell in between, would have lived and died in the time it took to cross that gap. New Horizons, the spacecraft that flew past Pluto in 2015, was launched at an even faster speed. At its peak, during its Jupiter gravity assist, it was moving at roughly 16.26 kilometers per second. But even New Horizons would take about 78,000 years to reach Alpha Centauri. And then there's the Parker Solar Probe. As of the mid-2020s, the Parker Solar Probe holds the record as the fastest human-made object ever built. During its closest approaches to the Sun, it reaches speeds of approximately 192 kilometers per second. That is nearly 700,000 kilometers per hour. At that speed, you could fly from New York to Tokyo in about 53 seconds. At the peak speed of the Parker Solar Probe, the fastest thing humanity has ever created, the journey to Alpha Centauri would take approximately 6,600 years. 6,600 years ago, the pyramids had not yet been built. Stonehenge did not exist. The Sumerians had not yet invented writing. The entire recorded history of human civilization would need to happen twice over before you arrived. And then there is light, the fastest thing in the universe, the cosmic speed limit, 299,792 kilometers per second. Nothing in the known universe travels faster than light, and light takes 4 years and 3 months to reach Alpha Centauri. Think about what that means. The light you see when you look at Alpha Centauri tonight left the star more than 4 years ago. You are not seeing the star as it is. You are seeing the star as it was 4 years and 3 months in the past. If Alpha Centauri exploded right now, at this exact moment, you would not know about it for more than 4 years. You would continue to see a calm, steady point of light in the sky, completely unaware that the star had already died. This also means that communication with anything at Alpha Centauri would face an agonizing delay. If you sent a radio message toward Alpha Centauri today, traveling at the speed of light, it would arrive in 4 years and 3 months. And if someone there sent a reply immediately, that reply would take another 4 years and 3 months to reach you. A simple exchange of hello and hello back would take 8.5 years. Imagine trying to have a conversation with that kind of delay. You say something, then you wait 8.5 years for a response, then you reply. Then you wait another 8.5 years. A dialogue that would take 5 minutes on Earth would take a lifetime at interstellar distances. Even at the speed of light, the fastest speed the universe permits, the distance between stars turns communication into an exercise in geological patience. There is something else worth understanding about this distance, something that makes it feel even more vast and empty. The space between our Sun and Alpha Centauri is not filled with anything. It is not like the ocean between continents, where there are islands and currents and marine life. It is not like the desert between cities, where there are oases and landmarks and roads. The space between stars is a vacuum, an almost perfect void, a darkness so empty that it makes the most barren desert on Earth look like a crowded marketplace. In the interstellar medium, the average density of matter is roughly 1 atom per cubic centimeter. 1 atom. In a volume the size of a sugar cube, you would find, on average, a single atom, usually hydrogen, sometimes a speck of dust. The rest is nothing. Pure, empty, silent nothing. If you could somehow fly through this space, you would see nothing around you. No landmarks, no waypoints, no sense of progress. Just blackness in every direction, with the stars ahead growing imperceptibly brighter and the sun behind growing imperceptibly dimmer. Over a journey that would last thousands or millions of years, depending on your speed. There would be no weather, no sound, no light except the distant pinpricks of stars. Just you and the void and time. This is the space we would need to cross to reach Alpha Centauri. Not a distance in the way we usually think of distance, but an abyss, a chasm of emptiness so profound that it challenges the very concept of travel. The measurement of this distance is itself one of the great achievements of astronomy. For most of human history, no one knew how far away the stars were. They were simply lights in the sky, hanging at some unknown height above the Earth. It was not until the 19th century that astronomers developed a technique precise enough to measure the distance to even the nearest stars. The technique is called stellar parallax. It works on the same principle you use when you hold up your thumb and close one eye, then the other. Your thumb appears to shift against the background because your two eyes are looking at it from slightly different angles. The closer your thumb is to your face, the more it appears to shift. Stars do the same thing. As the Earth orbits the Sun, moving from one side of its orbit to the other over 6 months, nearby stars appear to shift very slightly against the background of more distant stars. This shift is called parallax, and by measuring it, you can calculate the distance to the star using simple trigonometry. But the shift is incredibly tiny. Even for the nearest star, the parallax angle is less than 1 arcsecond, a unit so small that it is 1/3600th of a degree. Measuring it requires extraordinarily precise instruments and painstaking observations. The first successful measurement of stellar parallax was made in 1838 by the German astronomer Friedrich Bessel, who measured the distance to the star 61 Cygni, about 11 light-years away. But it was Thomas Henderson, working at the Royal Observatory at the Cape of Good Hope in South Africa, who measured the parallax of Alpha Centauri. His measurements, published in 1839, revealed that Alpha Centauri was the closest star system to the Sun, at a distance of roughly 4 light-years. Henderson's measurement was one of the most important discoveries in the history of astronomy. For the first time, humanity had a concrete, measured answer to the question of how far away the stars are. And the answer was sobering. Even the nearest star was unimaginably far away. The gulf between our sun and its closest neighbor was not a gap you could cross with any technology that existed or could be imagined in the 19th century. It was, for all practical purposes, infinite. And nearly 2 centuries later, that assessment has not fundamentally changed. Section 4. The Dream of Getting There. Humanity has never been good at accepting limits. We are a species that crossed oceans in wooden boats, that climbed the highest mountains, that flew through the air a mere 66 years after inventing powered flight, that walked on the moon within a single human lifetime of the first airplane. When someone tells us something is impossible, we take it as a challenge. So it should come as no surprise that for as long as we have known how far away the stars are, we have been dreaming of ways to get there. The challenge of interstellar travel is the greatest engineering problem our species has ever contemplated. It dwarfs everything else, from building the pyramids to splitting the atom to landing on the moon. And the ideas that have been proposed to solve it range from the elegant to the audacious to the barely sane. Let us go through them, one by one, from the technology we have now to the technology we might build, to the technology that might forever remain a dream. The most obvious starting point is chemical rockets. These are the engines that have powered every space mission in history, from the first V-2 rockets in World War II to the Saturn V that carried astronauts to the moon to the Falcon 9 and Space Launch System rockets of today. Chemical rockets work by burning fuel, usually liquid hydrogen and liquid oxygen, and expelling the hot exhaust gases at high speed. The reaction pushes the rocket forward, obeying Newton's third law of motion. For every action, there is an equal and opposite reaction. Chemical rockets are powerful. A Saturn V rocket produced 35 million newtons of thrust at liftoff, enough to shake the ground for miles around the launch pad. They can accelerate a spacecraft to the speeds needed to escape Earth's gravity, about 11 kilometers per second, and to travel between planets within the solar system. But chemical rockets have a fundamental limitation, and it is not one that can be solved by building bigger or better rockets. It is a limitation rooted in the laws of physics themselves. The problem is called the tyranny of the rocket equation. In 1903, the Russian mathematician Konstantin Tsiolkovsky derived a formula that governs all rocket propulsion. The formula says that the speed a rocket can achieve depends on two things: the exhaust velocity of the fuel and the ratio of the rocket's total mass, including fuel, to its empty mass after the fuel is burned. The exhaust velocity of chemical rockets is limited by the energy density of chemical bonds. The best chemical fuels, liquid hydrogen and liquid oxygen, produce an exhaust velocity of roughly 4.5 kilometers per second. This cannot be significantly improved. It is a hard ceiling set by chemistry. The mass ratio is where the problem becomes devastating. The rocket equation is exponential. To double the final speed of a rocket, you do not need to double the fuel. You need to square the mass ratio. To triple the speed, you need to cube it. This means that to reach very high speeds, you need absurdly, impossibly large amounts of fuel. To reach Alpha Centauri within any reasonable time frame, a spacecraft would need to travel at a significant fraction of the speed of light. Even 1% of the speed of light, 3,000 kilometers per second, would mean a journey of about 424 years. That is a long time, but it is within the range of a hypothetical generation ship. But to accelerate a modest spacecraft to 1% of the speed of light using chemical rockets, the mass ratio would be so extreme that the required fuel mass would exceed the mass of the observable universe. This is not an exaggeration. The numbers have been calculated. To push a single kilogram to 1% of light speed using chemical propulsion, you would need more fuel than exists in the entire cosmos. Chemical rockets are magnificent machines. They conquered low Earth orbit. They reached the moon. They sent probes to every planet in the solar system, but they cannot cross the interstellar gulf. They are rowboats, and the distance to Alpha Centauri is the Pacific Ocean. The next step up is ion propulsion. Ion drives work by ionizing a propellant, usually xenon gas, and accelerating the ions using electric fields. The exhaust velocity of an ion drive is much higher than a chemical rocket, typically 30 to 50 kilometers per second, roughly 10 times better. This makes ion drives far more fuel efficient, but there is a trade-off. Ion drives produce very little thrust. The Dawn spacecraft, which used ion propulsion to visit the asteroids Vesta and Ceres, produced a maximum thrust of roughly 90 millinewtons. That is about the force you would feel if someone placed a single sheet of paper on your outstretched palm. You would barely notice it. Over time, however, this tiny thrust adds up. An ion drive running continuously for months or years can gradually accelerate a spacecraft to impressive speeds. The Dawn spacecraft accumulated a total change in velocity of about 11 kilometers per second over its mission, comparable to what a chemical rocket could achieve in a single burn, but using far less fuel. For interstellar travel, ion drives are better than chemical rockets, but still hopelessly inadequate. Even with continuous operation over decades, an ion-propelled spacecraft would take tens of thousands of years to reach Alpha Centauri. Better than Voyager's 73,000, perhaps, but still measured in geological timescales rather than human ones. In the late 1950s, a group of physicists at General Atomics, a defense contractor in San Diego, proposed something far more radical. Their project was called Orion, and its concept was simple, elegant, and slightly insane. Instead of burning chemical fuel, Project Orion would propel a spacecraft using nuclear explosions. Not a reactor. Not a controlled fusion burn. Actual nuclear bombs detonated one after another behind the spacecraft, pushing it forward with each blast. The design called for a massive steel pusher plate at the back of the spacecraft, connected to the body of the ship by a system of shock absorbers. Nuclear bombs would be ejected from the rear of the ship and detonated a short distance behind the pusher plate. The force of each explosion would slam into the plate, and the shock absorbers would smooth out the impulse into a sustained acceleration. The physicist Freeman Dyson, who worked on the project, calculated that a large Orion spacecraft could reach speeds of 5 to 10% of the speed of light. At 5% of light speed, 15,000 kilometers per second, the journey to Alpha Centauri would take roughly 85 years. At 10%, it would take about 42 years, within a human lifetime. The first interstellar journey, achievable with technology that was fundamentally understood in the 1960s. The design was technically feasible. The physics worked. The engineering was challenging but not impossible. Test models using conventional explosives were successfully flown. The project had supporters at the highest levels of the United States government and military. But Project Orion had a problem. Several problems, actually. The first was the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear explosions in space. The second was the radioactive fallout that would be generated during launch, as the first few dozen detonations occurred within Earth's atmosphere. The third was a general unease about the idea of building a spacecraft powered by thousands of nuclear bombs. Project Orion was canceled in 1965. The most practical interstellar propulsion system ever designed was shelved, not because it did not work, but because the world was not ready for it. And 50 years later, it remains the most thoroughly studied and most technically feasible concept for fast interstellar travel. In the 1970s, the British Interplanetary Society picked up where Orion left off. Their project was called Daedalus, named after the mythical Greek craftsman who built wings of wax and feathers to escape imprisonment. Project Daedalus was designed as an unmanned interstellar probe, aimed at Barnard's star, about 6 light-years away. Unlike Orion, which used fission bombs, Daedalus would be powered by nuclear fusion, the same process that powers the Sun. Tiny pellets of a fuel mixture containing deuterium and helium-3 would be injected into a combustion chamber at a rate of 250 pellets per second. Electron beams would compress each pellet to the point of ignition, triggering a fusion reaction that would expel superheated plasma out the back of the ship. The numbers were extraordinary. Daedalus would be enormous, a spacecraft weighing 54,000 tons at launch, most of which was fuel. It would accelerate for nearly 4 years, reaching a peak speed of 12% of the speed of light, 36,000 kilometers per second. At that speed, it would cross the distance to Barnard's star in roughly 50 years. But there were 2 major problems. First, Daedalus could not slow down. It carried no deceleration stage. It would fly through the target star system at 12% of the speed of light, conducting observations during a brief flyby that would last only a few days. There would be no orbit, no landing, just a blur of data collected at impossible speed. Second, the fuel. Helium-3 is vanishingly rare on Earth. The Daedalus team proposed mining it from the atmosphere of Jupiter, using massive orbital platforms that would scoop up the gas and process it over decades. This was theoretically possible, but required an industrial infrastructure in the outer solar system that was far beyond anything humanity could build. Project Daedalus was never intended to be a blueprint for an actual mission. It was a thought experiment, a rigorous exercise in asking the question, could we build an interstellar spacecraft with known physics? The answer was yes, but only barely, and only at a cost that would strain the resources of an entire civilization. In 2016, a very different approach was proposed. One that did not involve giant spacecraft or nuclear engines or mining Jupiter for fuel. One that was, in many ways, the most creative and the most realistic interstellar concept ever devised. It was called Breakthrough Starshot. The announcement was made on April 12, 2016, by the billionaire physicist and investor Yuri Milner, alongside Stephen Hawking, the most famous scientist in the world. Their proposal was elegantly simple. Instead of sending one large spacecraft, send thousands of tiny ones. Each probe would be a starship, a wafer-thin spacecraft weighing roughly 1 gram. Just 1 gram, the mass of a paperclip. Each starship would carry a camera, a navigation system, a communication laser, and a tiny power supply, all integrated onto a single silicon chip a few centimeters across. Attached to each star chip would be a lightsail, a thin, reflective membrane about 4 meters on each side, made of a material so light that the entire sail would weigh only a few grams. The sail would not catch wind, it would catch light. On the ground, a massive array of lasers, totaling about 100 gigawatts of power, would be aimed at the light sail. The concentrated beam of photons would push the sail forward, accelerating the tiny probe at a force of roughly 60,000 times the force of gravity. In about 10 minutes, the star chip would reach 20% of the speed of light, 60,000 kilometers per second, 1/5 the speed of the fastest thing in the universe. At that speed, the journey to Alpha Centauri would take approximately 20 years. 20 years, not 73,000, not 6,600. 20. A probe launched when a child is born could arrive before that child is old enough to buy their own home. For the first time in the history of interstellar flight proposals, the travel time was measured in human terms. Breakthrough Starshot was not science fiction. It was based on real physics. Every component of the system, the chip, the sail, the laser array, was theoretically achievable with extensions of current technology. No new physics was required, no exotic matter, no warp drives, no violations of known natural law. Just engineering. Incredibly ambitious engineering, but engineering nonetheless. But the challenges were formidable. First, the acceleration. 60,000 Gs of force for 10 minutes is a brutal ride. The chip and the sail would need to survive accelerations that would crush a human being into paste. The sail, material, would need to reflect the laser light with extraordinary efficiency, because any energy absorbed would heat the sail, and at 100 gigawatts, even a small percentage of absorbed energy would vaporize it. The material would need to be incredibly light, incredibly reflective, and incredibly strong, all at the same time. Second, the interstellar medium. At 20% of the speed of light, even a tiny grain of dust becomes a lethal projectile. A speck of dust weighing 1/millionth of a gram, striking the star chip at 60,000 kilometers per second, would release energy equivalent to a small explosive charge. And the interstellar medium, while nearly empty, is not completely empty. Over a journey of 4 light years, the probability of hitting at least some dust grains is significant. The star chip would need shielding, or it would need to be lucky. Third, communication. A 1-gram chip at a distance of 4 light years needs to send data back to Earth. The communication laser on the chip would produce a beam so faint that detecting it would require a receiving antenna on Earth the size of a small city. The data rate would be agonizingly slow, perhaps a few bits per second. Transmitting a single photograph could take days or weeks. Fourth, the laser array itself. 100 gigawatts of laser power is roughly the total electricity consumption of the entire United States. Building a laser array of that power in a single location would be one of the largest engineering projects in human history. It would cost billions of dollars, possibly tens of billions. And fifth, the flyby problem. Like Daedalus, the star chip would not slow down. It would scream through the Alpha Centauri system at 20% of the speed of light, passing through the entire habitable zone of Proxima Centauri in a fraction of a second. All observations, all photographs, all measurements would need to be taken during a flyby, so brief that it would make New, Horizon's Pluto encounter, look leisurely. Despite all these challenges, Breakthrough Starshot remains the most credible near-term proposal for an interstellar mission. It does not require technologies that are centuries away. It requires technologies that are decades away. The difference is significant, and work is already underway on several of the key components, including ultralight sail materials, miniaturized sensors, and high-power laser arrays. If everything goes well, a prototype could be tested within the next 20 to 30 years. A full mission could be launched within 50. And the data from that mission, the first ever close-up images of another star system, could be received on Earth within 70 to 80 years from now. A timeline that is long by personal standards, but astonishingly short by cosmic ones. Beyond breakthrough starshot, there are more ambitious concepts. Concepts that require technologies we do not yet have, but that the laws of physics do, not forbid. One of the most elegant is the Bussard ramjet, proposed in 1960 by the physicist Robert Bussard. The idea is deceptively simple. Instead of carrying your fuel with you, you collect it as you go. The interstellar medium, while nearly empty, does contain hydrogen, roughly 1 atom per cubic centimeter. A ramjet equipped with an enormous magnetic scoop, hundreds or even thousands of kilometers across, could gather this hydrogen, funnel it into a fusion reactor, and use it as fuel. In theory, a Bussard ramjet could accelerate indefinitely, never running out of fuel because its fuel is the universe itself. It would sweep through space like a whale filtering plankton from the ocean, growing faster and faster as long as its engine burned. Given enough time, it could approach the speed of light. The concept inspired some of the most beautiful science fiction ever written. The writer, Poul Anderson, built his novel Tau Zero around a Bussard ramjet that could not stop, accelerating forever, the crew trapped inside as the universe aged and died around them. It was a haunting image, a ship that runs on the emptiness between stars. But the Bussard ramjet, like so many interstellar concepts, has a flaw. The drag created by scooping up interstellar hydrogen may actually exceed the thrust generated by burning it. The faster you go, the more hydrogen you encounter, but the more energy you lose to drag. At relativistic speeds, the scoop becomes a brake rather than a fuel collector. Later analyses have shown that a pure Bussard ramjet probably cannot work as originally envisioned, though hybrid designs combining a ramjet with stored fuel might still be viable. It is a beautiful idea, an engine that drinks the void, and even if it does not work in its purest form, it represents something important about the human approach to impossible problems. We do not accept them, we redesign them. Fusion propulsion is perhaps the most promising. If humanity can master controlled nuclear fusion, the same process that powers the sun, we could build engines of extraordinary capability. A fusion drive would use hydrogen isotopes as fuel, fusing them into helium and releasing enormous amounts of energy. The exhaust velocity of a fusion engine could reach several percent of the speed of light, making interstellar journeys of decades to centuries theoretically possible. The challenge is that we have not yet achieved sustained, controlled fusion on Earth. The International Thermonuclear Experimental Reactor, ITER, currently under construction in southern France, aims to demonstrate that fusion can produce more energy than it consumes. But ITER is a research facility, not a power plant, and the leap from a ground-based research reactor to a spacecraft engine that can operate for years in the vacuum of space is immense. Still, fusion is real physics. The sun does it every second of every day. If we can replicate it in a controlled, compact, efficient way, the stars become reachable. Not easy, not quick, but reachable. Then there is antimatter, the most potent energy source in the universe. When a particle of matter meets its antimatter counterpart, both are annihilated, and their entire mass is converted into energy according to Einstein's famous equation, E equals mc squared. The energy released by the annihilation of 1 gram of antimatter with 1 gram of matter is roughly equivalent to the explosion of a 43 kiloton nuclear bomb. Gram for gram, antimatter is the most efficient fuel conceivable. An antimatter-powered spacecraft could, in theory, reach speeds of 50 to 90% of the speed of light. At those speeds, Alpha Centauri would be reachable in 5 to 8 years. The journey would go from impossible to merely extraordinary. But there is a problem. Actually, several problems. First, antimatter does not exist naturally on Earth. It must be manufactured, one particle at a time, in particle accelerators like the ones at CERN in Switzerland. The process is staggeringly inefficient. The total amount of antimatter produced by all the particle accelerators on Earth since the technology was invented amounts to roughly 20 nanograms, 20 billionths of a gram. If you collected every antiproton ever made and annihilated them all at once, the energy released would not be enough to boil a cup of tea. Second, the cost. At current production rates and energy costs, 1 gram of antimatter would cost roughly $62 trillion. An interstellar mission would require several kilograms. The price tag would exceed the gross domestic product of the entire planet for several centuries. Third, containment. Antimatter cannot touch any form of ordinary matter, or it annihilates. You cannot store it in a bottle, because the bottle is made of matter. Antimatter must be suspended in a vacuum using electromagnetic fields, a technique called a penning trap. Current penning traps can hold tiny numbers of antiprotons for months at a time. Scaling this up to kilograms of antimatter is a challenge that borders on the fantastical. Antimatter propulsion is not impossible. The physics is sound. But the engineering required is so far beyond our current capabilities that it belongs not to the next century, but perhaps to the next millennium. There is another approach to interstellar travel that does not rely on speed at all. An approach that accepts the enormous distance and the long travel time and simply works around them. The generation ship. The concept is straightforward. If the journey takes centuries, then build a ship large enough to sustain a human population for centuries. Not a crew of astronauts, but a community, a village, a town, a small self-sustaining world, complete with farms, factories, schools, hospitals, and everything else needed to support human life indefinitely. The people who launched the ship would never see Alpha Centauri. Their children would never see it. Their grandchildren would never see it. The ship would become their world, their home, their entire universe. Generations would be born, live and die within its walls. And one day, after centuries of travel, the ship would arrive at its destination, and the people who stepped out onto a new world would be the distant descendants of the people who left Earth. Separated by dozens of generations, connected by nothing but the mission they inherited. The idea is romantic. It is also nightmarish. Consider the numbers. At 1% of the speed of light, the journey to Alpha Centauri would take 424 years. That is roughly 15 to 20 generations. At 1/10 of 1% of light speed, a more realistic velocity for a very large ship, the journey stretches to 4,240 years, over 100 generations. To sustain a human population over that many generations, you need genetic diversity. Studies on minimum viable populations suggest that you would need at least 10,000 people, possibly 40,000, to maintain enough genetic diversity to avoid the problems of inbreeding over centuries. You would need a ship large enough to house, feed, and provide for tens of thousands of people. The ship would need to recycle everything, air, water, waste, perfectly with zero net loss for centuries. You would need governance, laws, culture, education, medicine. You would need to maintain a technological civilization in a metal cylinder hurtling through the void, with no resupply possible, no help available, no margin for catastrophic error. A single failed system, a contaminated water supply, a structural breach, a pandemic, a civil war could end the mission and everyone aboard. And there is the ethical question. The people who are born on the generation ship did not choose this journey. They did not volunteer. They were born into it, locked into a metal world they cannot escape, committed to a destination they will never reach. Their lives are defined by a decision made by ancestors they never met. Is this ethical? Is it moral to commit your unborn descendants to a lifetime inside a spacecraft? These are not hypothetical questions. If humanity ever seriously contemplates a generation ship, these are the questions that will need to be answered. And the answers are not obvious. There is a concept in spacecraft engineering called the O'Neill cylinder, proposed by the physicist Gerard O'Neill in the 1970s. It envisions a pair of enormous rotating cylinders, each several kilometers long and a kilometer or more in diameter, spinning to create artificial gravity on the inner surface. Inside, you would have land, sky, weather, rivers, forests, towns, a self-contained world, a habitat that could, in theory, sustain thousands of people indefinitely. An O'Neill cylinder pointed at Alpha Centauri would be, in essence, a small planet on a very long road trip. The people inside would live ordinary lives. They would farm. They would teach. They would fall in love, grow old, and die. Their children would do the same, and their children's children. Generation after generation, the ship would drift through the darkness, carrying its population forward like an ark. But the psychological challenges are staggering. Imagine growing up knowing that your entire world is a metal tube, that outside the walls is an infinite void of nothing, that the destination your great-great-grandparents chose is still centuries away. Imagine knowing that you will never see a sunset that is not simulated, never feel wind that is not manufactured, never stand on ground that was not engineered. Your sky is a ceiling. Your horizon is a curve. Your entire reality is artificial. Some researchers have studied the psychology of long-duration isolation. Antarctic research stations, submarine crews, and International Space Station astronauts have all provided data on how humans cope with confinement and monotony. The results are mixed. Some people thrive. Others deteriorate. Depression, interpersonal conflict, and a condition called third quarter syndrome, a psychological low point roughly 3/4 of the way through a mission, are common. On a generation ship, there is no third quarter syndrome, because there is no end point in any individual's lifetime. The psychological burden is not the weight. It is the knowledge that the weight will outlast you, that you are, in a very real sense, a means to an end, a link in a chain. Your purpose is not to arrive, but to keep the chain unbroken so that someone, someday, will. Whether human psychology can sustain that kind of purpose over centuries is one of the deepest unanswered questions in the entire field of interstellar travel. And then there is the most exotic concept of all, the one that sounds like pure science fiction but is, in fact, based on a rigorous solution to Einstein's field equations of general relativity, the Alcubierre warp drive. In 1994, a Mexican physicist named Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity that described a theoretical method for faster-than-light travel. Not by moving a ship through space faster than light, which is forbidden by special relativity, but by moving space itself around the ship. Alcubierre's concept works like this. Imagine a bubble of flat, normal space surrounding a spacecraft. In front of the bubble, space is contracted, compressed, squeezed together. Behind the bubble, space is expanded, stretched apart. The bubble itself, carrying the ship inside it, moves through the surrounding space at any speed, including speeds faster than light. The key insight is that while nothing can travel through space faster than light, space itself has no speed limit. The universe itself expanded faster than light during the inflationary period after the Big Bang. Galaxies beyond the observable horizon are receding from us faster than light right now, not because they are moving through space that fast, but because the space between us and them is expanding. Alcubierre showed that this same principle could, in theory, be harnessed to move a ship. The ship inside the bubble is not moving through space at all. It is stationary within its bubble of flat space-time. The bubble is what moves, carrying the ship with it the way a surfer is carried by a wave. The mathematics is valid. The solution satisfies Einstein's equations. But there is a cost, a horrifying cost. To create the warp bubble, you need a form of energy called negative energy or exotic matter. This is not ordinary matter or energy. It is a substance with negative energy density, meaning it gravitationally repels rather than attracts. Exotic matter has never been directly observed, although some quantum effects, like the Casimir effect, produce tiny amounts of negative energy density under specific conditions. In Alcubierre's original calculations, the amount of exotic matter required to create a warp bubble large enough for a spacecraft was approximately equal to the mass energy of the planet Jupiter. That is an absurd amount of energy, far beyond anything humanity could ever produce. Over the years, other physicists have refined the concept. In 1999, Chris van den Broek found a way to reduce the energy requirement by making the bubble very small on the outside, but large on the inside, a kind of space-time origami. Harold White, a physicist at NASA's EagleWorks laboratory, proposed in 2011 that adjusting the shape of the bubble could reduce the energy requirement to roughly 700 kilograms of exotic matter. Still an enormous amount, but at least a finite one. In 2021, Eric Lentz at the University of Göttingen published a paper proposing warp drive solutions that used only positive energy, eliminating the need for exotic matter entirely. The physics community received this with interest and skepticism in equal measure. The calculations were complex, and whether they could be translated into any practical technology remained deeply uncertain. The Alcubierre warp drive remains a theoretical possibility. It is not forbidden by the laws of physics as we currently understand them. But building one would require manipulating space-time in ways that are so far beyond our current capability that it may remain forever in the realm of mathematics and thought experiments. Or, perhaps centuries from now, a civilization far more advanced than our own will figure out how to bend space around a ship and make the stars as accessible as the next continent. For now, it is a beautiful dream, the most beautiful dream in physics. Section 5. What would we find? We have spent the last sections confronting the distance and the difficulty of crossing it. We have tallied the years and the trillions of miles. We have weighed the rocket equations and the exotic matter and the generation ships full of unborn children. Now, for just a few moments, let us do something different. Let us pretend we made it. Let us imagine that somehow, through some combination of genius and stubbornness and time, humanity found a way. Let us imagine you are aboard a spacecraft approaching the Alpha Centauri system. The journey is over. You are here. What would you see? Let us slow down for this part. Let us take our time. Because this is the moment that every dreamer, every scientist, every child who ever pointed at a star and asked, "Can we go there?" has imagined. The arrival. Your ship is decelerating. The engines, whatever miraculous technology powers them, have been burning in reverse for weeks or months, shedding the enormous velocity that carried you across 4 light years of void. Through the forward viewport, the stars have shifted. They no longer appear as streaks of light smeared by your velocity. They have resolved back into individual points, and 3 of those points are growing brighter. The Alpha Centauri system is ahead. 2 brilliant stars, 1 golden and 1 amber, separated by a gap that widens as you approach. And somewhere nearby, too faint to see yet against the glare of its larger companions, is the dim red ember of Proxima Centauri. You have spent years in transit, perhaps decades. Perhaps you were born during the journey, if this is a generation ship, and the Earth you are leaving behind is a place you have never seen except in photographs and data files. Or perhaps you were frozen, suspended in some form of cryogenic sleep, and the last thing you remember before waking is the blue curve of Earth receding behind you. Either way, you are here, the first human being, or the first human generation, to see another star system from the inside. The first thing you would notice as your ship decelerated and the stars resolved from streaks of light back into individual points is that the sky looks different here, not dramatically different. The constellations you know from Earth are mostly intact, because the stars that form them are so far away that a shift of 4 light years barely changes their apparent positions. Orion still looks like Orion. The Big Dipper still looks like the Big Dipper, but there is one constellation that has changed. One new star has appeared where none existed before. A moderately bright, yellowish star in the constellation Cassiopeia. That star is the Sun. Our Sun, seen from Alpha Centauri, would appear as a 0.5 magnitude star, roughly as bright as the star Betelgeuse appears from Earth. It would be clearly visible to the naked eye, but not particularly remarkable. Just another point of light among thousands. You could cover it with your thumbnail, the home of every human who has ever lived, every war fought, every symphony composed, every child born, every sunrise and sunset and midnight conversation. All of it, reduced to a dim yellow dot in an unremarkable constellation. No different, to an observer here, than any of the other specks of light scattered across the sky. It is a strange feeling, imagining this. A mixture of insignificance and wonder. The sun, which looms so large in our lives, which governs our seasons and our crops and our daily rhythms, is nothing special from here. It is a middle-aged, medium-sized, ordinary star, one of 400 billion in the galaxy. Visible from the nearest star system, but barely noteworthy. Carl Sagan wrote about this perspective. He called it the humbling and character-building experience of seeing our world from far away. And he was right. There is something about seeing your home reduced to a speck that changes the way you think about everything. As your ship approaches closer, the Alpha Centauri system begins to reveal itself. Two bright stars, Alpha Centauri A and B, dominate the view. They are separated by a gap that varies over their 80-year orbit, but at a typical distance, they appear as two distinct, brilliant points of light. One golden yellow, the other slightly orange, like two jewels set against the blackness. If you happen to arrive when the two stars are near their closest approach, about 11 astronomical units apart, they would present a breathtaking sight. Two suns, close enough that from a planet orbiting either one, the other would appear as a brilliant star, far brighter than any planet in our own sky. Venus, the brightest object in Earth's night sky besides the Moon, has an apparent magnitude of about minus 4.6. Alpha Centauri b, seen from a planet orbiting Alpha Centauri A at Earth's distance, would shine at roughly minus 21 magnitude during close approach, bright enough to read by. Bright enough to cast sharp double shadows on the ground. Two suns, two shadows. A world bathed in light from two directions. It is a scene that belongs in science fiction, but it is how a real world in this system would look. And then, far from the brilliant binary pair, separated by a vast gulf of space, you would find Proxima Centauri, dim, red, barely visible against the stars. A faint ember glowing in the darkness, 12,950 astronomical units from the binary pair it orbits. If Alpha Centauri A and B are a campfire, Proxima is a distant match flame, flickering in the night. Approaching Proxima, you would see its planets, and the most important of them, Proxima b, would slowly come into view. A small, rocky world, roughly the same size as Earth, orbiting so close to its red dwarf star that its year lasts only 11 days. What would Proxima b look like from orbit? It depends on many things we do not yet know. Does it have an atmosphere? Does it have water? Does it have life? In the most optimistic scenario, Proxima b has a thick atmosphere, perhaps rich in nitrogen and carbon dioxide, with water vapor and clouds. From orbit, you might see a world half in light and half in darkness, with a narrow band of twilight between them. The day side would glow with a deep, reddish hue, bathed in the constant light of Proxima Centauri. Clouds might swirl along the terminator zone, where warm air from the day side meets cold air from the night side. Perhaps you would see glints of liquid on the surface, lakes or seas reflecting the dim red light. In a less optimistic scenario, Proxima b might look more like Mars, a barren, airless rock scarred by billions of years of stellar flares, its surface irradiated and sterile. No atmosphere, no water, no hint of life. Just rock and dust and the cold silence of a world that might have once had a chance but lost it to the fury of its star. The truth is, probably, somewhere in between. But we will not know until we go there. Or at least until we build telescopes powerful enough to read the chemical signature of its atmosphere from 4 light-years away. Let us stay with the optimistic scenario for a moment. Let us imagine that Proxima b does have an atmosphere, that it does have water, that there is a narrow strip around the terminator zone where conditions are mild enough for liquid water to exist on the surface. What would it be like to stand there? The first thing you would notice is the light. It is not like sunlight on Earth. It is dimmer, much dimmer, and it is red. Proxima Centauri emits most of its energy in infrared wavelengths, with the visible light shifted toward the red end of the spectrum. To your eyes, the world would look like a perpetual deep sunset. The sky, if there is a sky, would not be blue. It would be some shade of red or orange or dark amber, depending on the composition of the atmosphere. The star itself would hang on the horizon, never rising, never setting. Because Proxima b is tidally locked, Proxima Centauri occupies a fixed position in the sky from any given point on the surface. In the terminator zone, the star would sit right on the horizon, half visible, half hidden, casting long, ruddy shadows across the landscape. It would be roughly 3 times the apparent diameter of our Sun, because Proxima b orbits so much closer to its star. But it would appear much dimmer, a large, dark red disk rather than the brilliant white-gold circle we are used to. The temperature in the terminator zone might be surprisingly moderate. Models suggest it could range from roughly -20 to +30 degrees Celsius, depending on atmospheric thickness and composition. Cold, but not impossibly cold, within the range of some of Earth's harshest environments. Arctic researchers and Antarctic expeditioners have lived and worked in comparable temperatures for extended periods. The wind would be constant. Atmospheric circulation models predict strong, persistent winds blowing from the cold night side toward the warm day side, driven by the temperature differential between the two hemispheres. These winds might reach hurricane force in some areas, or they might be moderated by mountains, valleys, and other surface features. Near the surface, in sheltered valleys along the terminator, the air might be still enough to breathe, if the atmospheric composition allowed it. And the sky. Oh, the sky. From the night side of Proxima b, facing away from the star, you would see a sky of extraordinary beauty. With no light pollution, no atmospheric scattering of starlight, the stars would burn with a ferocity that no human on Earth has ever witnessed, not even from the darkest desert or the most remote mountaintop. And among those stars, in the constellation Cassiopeia, you would find a small, yellowish point of light. Home. There is something unbearably poignant about that image, standing on a world 4.24 light-years from Earth, looking up at the stars, and finding the sun. Knowing that everyone you have ever loved, everyone who has ever lived, every moment of every human life, happened right there, on a tiny rock orbiting that faint yellow dot. And knowing that the light you are seeing left that star 4 years ago. That the Earth you are looking at is not the Earth of this moment, but the Earth of 4 years past. That anything happening at home right now, any birth or death or war or peace, is already over, already history, and you will not learn about it for another 4 years and 3 months. The distance is not just physical, it is temporal, it is informational, it is emotional. You are separated from home not just by 25 trillion miles of vacuum, but by 4 years of silence. 4 years of not knowing. 4 years in which anything could happen, and you would have no way of finding out. If you sent a message home, a simple 3-word message saying, "I am here," it would take 4 years and 3 months to arrive. And the reply, the simple 3-word response saying, "We hear you," would take another 4 years and 3 months to reach you. 8.5 years, round trip, for 6 words. The loneliest conversation in the history of our species. This is the reality of interstellar distance. It is not just about miles. It is about the profound, irreducible isolation that comes from being so far away that even light, the fastest messenger in the universe, takes years to deliver a single sentence. But perhaps the most extraordinary thing about standing on Proxima b would not be the view. It would be the question: is there life here? We do not know. We cannot know, not yet. But the question is not as far-fetched as it might seem. Life on Earth has proven extraordinarily resilient. Organisms thrive in boiling hot springs, in frozen Antarctic ice, in the crushing darkness of the deep ocean floor, in the radioactive cooling pools of nuclear reactors. Life, once it takes hold, is astonishingly difficult to extinguish. And Proxima b has had time. Billions of years. Proxima Centauri is roughly 4.8 billion years old, about the same age as our Sun. If conditions on Proxima b were ever suitable for life, even briefly, even in a small pocket along the terminator zone, life may have had enough time to take hold and to adapt, even to thrive. It might not look like anything we recognize. Life on a tidally locked world, bathed in red light, buffeted by constant stellar flares, would have evolved under pressures very different from those on Earth. Plants, if they exist, might not be green. They might be black, optimized to absorb every photon of the dim red light. Animals, if they exist, might have senses we cannot imagine, tuned to wavelengths of light and vibrations of air that are meaningless to human perception. Or there might be nothing. Just rock and silence and the eternal, ruddy glow of a dim red star. Either way, the answer would change everything. If life exists on Proxima b, it would mean that life is common in the universe. That the chemistry of life is not a fluke, but a tendency, something that the universe does routinely, given the right conditions. It would mean that the cosmos is not empty, that the silence of the stars is not the silence of a dead universe, but the silence of a vast, living one, too spread out and too far apart for its inhabitants to meet. And if Proxima b is dead, if its surface is sterile and its oceans, if it ever had oceans, have long since boiled away or frozen solid, that answer too would be meaningful. It would tell us something about the rarity of our own existence, about the extraordinary chain of events and conditions that conspired to produce a living world here, around our own sun, and not there, around the nearest one. Either way, we learn. Either way, we grow. Either way, the journey would be worth it. Section 6. The Beautiful Prison. And so we return to where we began, to the night sky, to the small golden point of light in the constellation Centaurus, to the star that is so close and so impossibly far away. We have traveled in our minds to Alpha Centauri tonight. We have met its 3 stars, the golden twin of our sun, the orange companion, and the dim red ember that is actually the nearest. We have explored the planet that orbits Proxima Centauri, a world of permanent twilight and crimson light that may or may not harbor the conditions for life. We have confronted the distance, that soul-crushing, mind-bending, 25 trillion-mile abyss of nothingness that separates us from the nearest star. We have dreamed of crossing it, with nuclear bombs and laser sails and fusion engines and bubbles of warped space-time. And we have imagined arriving, standing on alien soil, looking back toward home, and seeing our sun as just another star. And the question that remains, the question that underlies all of this, is a simple one. Will we ever go? The honest answer is we do not know. The distance is immense. The technology is not ready. The cost would be staggering. And the journey, even under the most optimistic scenarios, would take years or decades or centuries, depending on the method. But here is what we do know. We know that the laws of physics do not forbid it. There is no law of nature, no fundamental principle, no cosmic regulation that says a spacecraft cannot cross the distance between our Sun and Alpha Centauri. It is not forbidden. It is merely very, very difficult. And history has shown again and again that what is very difficult today can become routine tomorrow. In 1903, the Wright brothers flew a powered aircraft for 12 seconds. 66 years later, Neil Armstrong walked on the moon. In 1945, the first electronic computer filled an entire room and could perform a few thousand calculations per second. Today, the phone in your pocket performs billions. The gap between impossible and routine is often smaller than it appears. This does not mean that interstellar travel will happen soon. It may take centuries. It may take millennia. It may never happen at all if humanity cannot solve its problems here on Earth long enough to invest in the technologies required. But the possibility exists. The door is not locked. It is merely very, very heavy. And perhaps there is a deeper lesson here. A lesson not about technology or physics or engineering, but about what the distance itself means. The universe has placed the stars just far enough apart that reaching them requires a civilization to be patient, to be wise, to be cooperative, to invest not for the benefit of those alive today, but for the benefit of those who will be alive in decades or centuries. Interstellar travel is not a project for a nation or a corporation or a generation. It is a project for a species. A project that requires us to think on timescales that are fundamentally inhuman. Perhaps that is the point. Perhaps the distance between stars is not a prison. Perhaps it is a test, a filter, a way that the universe ensures that only civilizations that have learned to live with themselves, to overcome their short-term impulses, to invest in the long future, are rewarded with the stars. In our earlier videos, we explored the Fermi paradox, the great silence that hangs over the cosmos like a question mark. Where is everyone? Why, in a galaxy of 400 billion stars, have we found no evidence of other civilizations? Perhaps this is part of the answer. Perhaps many civilizations arise, look at the distances, do the math, and despair. Perhaps they turn inward, consumed by their own problems, their own conflicts, their own limitations. Perhaps they never muster the patience, the unity, the sustained will that interstellar travel demands. Perhaps they flicker and die, like candles in a draft, having never reached beyond their own solar system. And perhaps the civilizations that do survive, the ones that endure long enough to cross the interstellar gulf, are so rare, so scattered, and so patient that we simply have not encountered them yet. Perhaps the silence is not evidence of death. Perhaps it is evidence of patience, a galaxy full of civilizations that are waiting, working, slowly building the ships that will one day carry their descendants to the stars. There is one more thing worth saying tonight, something that is easy to lose sight of in all the talk of distances and speeds and propulsion systems. We do not need to physically travel to Alpha Centauri to learn about it. The James Webb Space Telescope, orbiting the Sun 1.5 million kilometers from Earth, is already studying the atmospheres of distant exoplanets, reading the chemical fingerprints of worlds orbiting other stars. Future telescopes, like the Habitable Worlds Observatory planned for the 2030s, will be specifically designed to image Earth-like planets around nearby stars and search for signs of life. The extremely large telescope, under construction in the Atacama Desert of Chile, will have a primary mirror nearly 40 meters across, capable of resolving details that no previous telescope could see. With these instruments, we can study Proxima b from here. We can analyze the light that passes through its atmosphere, searching for oxygen, methane, water vapor, ozone, the chemical signatures of a living world. We can measure its temperature, estimate its cloud cover, map its surface features. We can learn, from 4 light-years away, whether the nearest exoplanet is a dead rock or a living world, without sending a single spacecraft. This is one of the most remarkable achievements of human civilization. We cannot cross the distance. Not yet, but we can see across it. We can read the starlight and extract its secrets. We can, from the surface of our small planet, study worlds that orbit other suns and answer questions that our ancestors could not even formulate. The universe gave us the distance, but it also gave us the light, and the light carries information. Every photon that reaches our telescopes from Alpha Centauri is a message, written in wavelengths and absorption lines and spectral signatures, telling us about the temperature and composition and behavior of objects 4 light-years away. The universe is not silent. It is speaking to us constantly. We just need to learn how to listen. And perhaps that is the most beautiful resolution to the paradox of interstellar distance. We are trapped, yes. The gulf between stars is vast and cold, and probably uncrossable within our lifetimes. We may never set foot on Proxima b. We may never see Alpha Centauri with our own eyes from anything closer than 4 light-years. But we are not blind. We are not ignorant. We can look up at the sky and know, with scientific certainty, what those tiny points of light are. We know their masses, their temperatures, their compositions, their ages. We know how far away they are. We know how they were born and how they will die. We can detect their planets and study their atmospheres and search for signs of life. No other species on this planet can do that. No other species, as far as we know, in this entire galaxy can do that. We are a species of stargazers, born on a small planet orbiting an ordinary star, who somehow taught themselves to read the universe like a book, page by page, star by star, light year by light year. And if that is not a form of reaching the stars, then what is? It is late now. We have traveled a long way tonight, from the quiet field where we began, lying under the stars, to the nuclear fires of a triple star system 4 light-years away, to a tidally locked planet bathed in red light, to the engineering dreams of laser sails and warp drives, to the deep, silent void between here and there. And now it is time to come home. The stars are still out there. Alpha Centauri is still there, glowing softly in the southern sky, the nearest of all the distant lights. It is 4.24 light-years away, 25 trillion miles, an ocean of nothing that might take us 73,000 years to cross, or 20 years, or perhaps someday, no time at all. But tonight, it does not matter how far it is. Tonight, what matters is that it is there, that it exists, that somewhere, 4 light-years away, a small red star is burning quietly in the darkness, and a rocky planet is orbiting around it, and the light from that star is traveling through the void right now, crossing the emptiness at 300,000 kilometers per second, and in 4 years and 3 months, some of that light will reach this planet, and if you happen to be outside on a clear night, looking up, you will see it. A tiny point of light, the closest star. An entire world, maybe, with skies and seasons and storms of its own. Right there, almost close enough to touch. Almost. There is a line from the astronomer Carl Sagan that feels appropriate tonight. He once said that we are a way for the cosmos to know itself. And standing here, in our minds, at the edge of another star system, looking back at the tiny yellow dot that is our sun, you can feel the full weight of that statement. We are not separate from the universe. We are made of it. Every atom in your body was forged inside a star that died before the sun was born. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was manufactured in the nuclear furnaces of ancient suns and scattered across space in violent supernova explosions billions of years ago. You are, in the most literal and scientific sense, made of stardust. And when you look at Alpha Centauri, you are stardust looking back at a star. This is not poetry. This is chemistry. This is physics. This is the documented, verified, measured truth about what you are and where you came from. And it means that the distance between you and Alpha Centauri, as vast and as cold and as empty as it is also, in a very real way, a distance within yourself. You are the universe contemplating its own geography. You are matter and energy, arranged in a pattern complex enough to wonder about other arrangements of matter and energy, burning quietly 4 light years away. And that wondering is itself extraordinary. In a universe that is mostly hydrogen and helium and darkness, the fact that anything can wonder about anything is the rarest and most improbable event imaginable. More improbable than the formation of a star. More improbable than the assembly of a planet. More improbable, perhaps, than life itself. Consciousness is the universe's way of looking at itself and asking, what else is out there? Alpha Centauri does not know we are looking at it. Proxima b, if it has oceans and clouds and wind, does not know that a civilization 4 light years away is dreaming about visiting it. The stars do not care. The void does not care. But you do, and that caring, that curiosity, that stubborn, irrational, magnificent insistence on looking up and asking questions is the most remarkable thing in the known cosmos. Let the distance hold you tonight. Not as a source of frustration, but as a source of wonder. The universe is vast, and we are small, and the spaces between the stars are so immense that they defy comprehension. But you are here. You are aware. You are a part of this cosmos, a part of this grand, strange, beautiful arrangement of matter and energy that has been unfolding for 13.8 billion years. And somehow, against all odds, you are a part of it that can wonder about the rest. Close your eyes now. Let the numbers fade. Let the light years and the trillions of miles dissolve into the quiet darkness behind your eyelids. You do not need to solve the high problem of interstellar travel tonight. You do not need to cross any oceans of void. You do not need to reach for anything at all. Just breathe, and know that the stars are patient. They have been burning for billions of years. They will burn for billions more. They are not going anywhere, and neither are your dreams of reaching them. Alpha Centauri will be there tomorrow night, and the night after that, and the night after that, waiting, glowing, the closest star, the nearest world, a light in the darkness that has been shining since before the earth was born, and will continue to shine long after everything you have ever known has turned to dust. And that is enough. That has always been enough. Good night, and in your dreams walk among the stars. They are closer than you think.